Good evening. Am I audible? Could you please confirm if I'm audible? Uh, Please confirm if I'm audible. Uh, can you hear me? Hello. Uh, could you please confirm if I'm audible?
Yes, sir.
Okay, yeah, fine. Thank you. So let's start the live session for week 10 for the course Introduction to Semiconductor Devices taught by Professor Naresh Kumar Imani from IIT Hyderabad. And I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be taking similar assignment problems from week 10 that will be helping you in solving some of the problems that have been given to you in this week 10 assignment. And apart from that, we'll be covering some of the concepts that are required to build more knowledge towards this particular week's content. So, like, we are almost at the end of this course now. We have covered each and every aspect of, first of all, the basic physics that we have for any doped or undoped semiconductor. Then we went to some of the junctions, including the oxide, metal oxide semiconductor, oxide junctions, even metal semiconductor junctions we have discussed in brief, that are Schottky and Ohmic. And apart from that, like mainly the focus was from the past 2 or 3 weeks, the main focus is on the metal oxide semiconductor field effect transistors that are MOSFETs. Uh, the first we discussed what is a MOS capacitor, and then we went into what is a MOSFET. And since now the technology is evolving, as you all might be knowing about the technology scaling, if you are like a very basic nerd about these technologies, so you might be aware that we are going on for reducing the channel length so that we have come into the regime for even in nanometers. So due to these technology scaling, there are several problems that comes into that device, which we call as the short channel effects, that will be covering basically in this week's lecture. And these short channel effects includes velocity saturation, channel length modulation, drain induced barrier lowering, some of the differences in IV characteristics, how do the IV change if I take a long channel or a short channel MOSFET, and some of the, like, a very basic overview of the modern field effect transistor, which are also called as FinFETs, nanowires, tunnel FETs, and there are more such as nanosheets, etc. You might have heard of it, but like we'll be taking a very basic overview of these technologies also, that how they are helping or how they are basically uh, trying to achieve what we want to. So so let's start with a very basic summary of the last class. In last class, what we did is we did the derivation, I guess, for the N-channel MOSFET, and we saw what are the different regimes when it comes. So, like, we took the ideal case that we have different current cases. Current is zero when we don't have any gate voltage, which is more than the threshold voltage, and this region we are calling it as cutoff, since there is no channel formed or the inversion layer. I hope you are aware of these terms now. If you have any doubt, you can stop me anytime and ask. Then we did the analysis for the linear regime, in which after deriving what we got to know that it is almost a linear function of the drain voltage, because the drain voltage is very less. So this particular square terms becomes negligible, and for this the condition is that the drain to source voltage should be less than the difference between VGS minus VT. And obviously now for all the conditions, VGS will be greater than VT. Only then it will conduct. This region, what we were calling it as linear or triode region, here the MOSFET acts as a resistor because it is linearly varying with the voltage. And at last what we saw is, we saw the final relation, which was something like this, which is VGS minus VT whole square. When this VDS basically becomes equals to VGS minus VT, which is the overdrive or the VD set, what we call as the overdrive voltage. We also derived this, and we got to know that there is a pinch off that is happening when the transistor is coming You can hear me, right?
Yes, sir.
Okay, so is
But the
my
screen seems to be paused.
yeah, yeah, I can see that. Maybe give me a moment. There's something. Uh, uh, is it visible now?
Yes, sir.
Yeah,
Screen
yeah,
has updated.
yeah. Thank you. So this was the overdrive voltage that I was talking about, and this region is what we call as saturation. Basically, why saturation? Because the current value is basically has saturated, irrespective of increasing the drain to source voltage. And this thing, the condition is the drain to source voltage should be greater than VGS minus VTH. So this is a very basic summary of all the regions of MOSFET and how do we get this. And we do know now that this is, if I ask you to make the ID versus VGS curve, so below threshold there is almost zero current, and once we reach the threshold voltage, we have something like this. And if I talk about the IDS versus VDS plot, which will be more easier to understand. So before the VD set voltage, we have something linear and then it kinds of saturates. So this is I'm making for an ideal MOSFET. So this is what is saturation region, this is what is linear, and it is certain voltage which is VGS which is greater than VT. And if I make less than VT, then it will be a very like a very less value, and I'm not drawing it because for an ideal case it will be exactly zero. So these were some of the equations. Okay, why is the variation in ID with respect to VD saturation more prominent? Okay, you are asking that for a higher VGS, let's say like this. So what exactly is the question? Could you please
So my
elaborate?
question is, practically, the graph is not straight in saturation, right?
Yes, yes,
It will have certain slope
yes,
due to the lambda factor coming,
yes, yes.
and that slope actually varies as VG increases, right? Slope is more steeper for higher VGS.
Slope is more steeper for. Oh, okay. Maybe what you're trying to say is this is more steeper for a higher VG and it is lesser for a smaller VG. Something like this.
Yes. Why could it be so? What could be the physics behind that?
Okay, fine, fine. So, like, I'll be covering this lambda factor, which is nothing but the channel length modulation. So, I'll be explaining this particular topic that will give you a better grasp of why it is happening like that. So, just like wait for this part to come, and then
Okay.
I'll let you know. So, as you already mentioned, now we have certain short channel effects that come into the picture. So, first one is nothing but this channel length modulation, in which what happens is this current exactly not remains uh, equals to a constant value, or it is not exactly saturated, and it becomes a certain function of VDS as we go into the saturation region, and some kind of a linear function. So this will come under one of the short channel effects. So before going into that, I want to cover a very brief topic, which is the effect of body bias on the MOSFET, because till now we have not discussed about the body bias effect. We have always kept our device the body terminal to a ground. So basically we have left this thing. So let me cover this up. This will take not more than 5 6 minutes. So let's say we have a MOSFET, again enhancement, let's say, because that will be better. So this is, let's say, oxide, and we have this gate. Let's say this is n plus source, this is n plus drain, and we have this body which is always grounded in general, that we have seen in all of the analysis that we have done till now. So I've considered NMOS. NMOS means p-type substrate, and let us say that we have a certain voltage which is VSB. So uh, can you tell if VSB is greater than 0, then what will be the condition of this particular diode, which is N plus and P? So if source has a higher voltage than the body, then what will happen? The junction will be in forward.
Reverse bias.
Yeah. So if I give a more positive voltage or at the source, and this is N side and the body is P side, so if we have a source voltage more, so it will be reverse bias. That is correct. And the opposite goes with, if the source voltage is negative, the body voltage is positive, then it will be forward bias. So what in general we do is we apply a certain body bias, let's say. So now till now what we were doing is we were keeping the body bias to ground, which is not the case, and now I am applying certain body bias. So the analysis in general we do is by applying a negative body bias such that this VSB remains positive. So what I have done is, let's say I have applied a body bias which has a certain negative value. Does it make sense? It is not confusing, right?
Which means source is at ground.
Yeah, you can say source is at ground and the body is getting a more and more negative voltage. Or you can say, like if I try to explain in very simple words, we have a higher voltage here and a lower voltage here.
Okay, sir.
Yeah, but I'm changing the body voltage. The source is always at ground. So once it happens, so as we have already seen, once it is positive, the MOSFET is in, oh sorry, the PN junction that we have here, it is in reverse bias, right? So if it is reverse bias, so now what we will have, like we have read that to have this inversion layer for a MOSFET, the minimum surface potential that we need to have is 2 phi f. But if I am giving it additional negative bias voltage, so we need to add up this particular voltage to have the inversion, because ultimately what we require is VGS should become greater than VTH. And at inversion, what will be requiring, we'll be requiring this additional VSB. So what I can write is, the surface potential that now I will be requiring will be plus VSB. And if VSB is positive, then what we can say is, I've already told that the PN junction is in reverse bias, and any electron near the surface, so let's say I'm talking about this surface, it will migrate towards the source. I hope you understand, because we are applying a negative bias, so it will migrate. Any electron that we will have is migrating towards the source to get the inversion, and the surface potential becomes whatever the potential that I have applied. So the main thing that we need to see the effect on is the effect on threshold voltage. So once we apply a body bias, what is the effect on threshold voltage? So even without doing any analysis, can you tell whether the threshold voltage will increase or decrease if this is the case?
It will
Uh,
increase.
it will.
Increase
Okay, so if VSB is positive, you are saying the threshold voltage will increase. Can you elaborate why do you think that?
because earlier for inversion we just needed to have phi s equals 2 phi f. Now we need to have 2 phi f plus VSB.
Exactly.
Need
So
to compensate for that also.
yes, exactly. So if you remember, we did this derivation also, that the the VTH, the threshold voltage is nothing but when this VGS is turning on. I hope you remember we did certain steps in which we started from that this particular voltage. So now I'm writing VGB because we have a body in picture. It was nothing but the flat band voltage plus then we depleted the carriers, which was Q depletion, and at last we added the surface potential, which was basically 2 phi f for the ideal case. So this is what we have, and this is what we wrote equals to the, if you remember, this is what was the threshold voltage. So VFB is nothing but phi ms minus the trapped charges. So I'm ignoring the QSS dash for now, neglecting these. So very basic. And if you remember, the Q depletion was nothing but 2 epsilon s QNA. Then there was a term called as surface potential here. So I'm writing phi s only. Yeah, and then plus 2 5f. So this was ideal case. So I'm trying to explain mathematically also. So this is nothing but the VTH. So now what I can write is, now this particular thing will become VGB plus this additional voltage that we require. And if I try to write it in very simple words, so it will be phi ms, and this 2 phi f, sorry, this psi s will change to 2 phi f plus VSB, and this is by Cox, and this additional surface potential will be phi f, oh sorry, 2 phi f plus VSB. So this is nothing but VTH. So as VSB is greater than 0, VTH increases, basically to compensate that additional voltage. So this is a very basic explanation of that. And if I like go very deeper, so what will happen, this is reverse bias, right? So we are having, for more and more reverse bias voltage, we will have more and more larger depletion width, and these junctions will be resulting in a very smaller effective length. So this is a channel length before any applying any negative bias, and this is after length. So sorry, after applying any negative bias. So we have a effective decrease in the channel length, and that is basically what will be resulting into increase in the current. As you know that this effective length comes into the denominator of this particular formulas also. So like this is a very basic explanation that was left, I guess, in the previous lectures. So now coming to the main point for this particular lecture, um, that is nothing but the short channel bits. Okay, so can anyone tell basically what is a short channel? Like how do we compare whether the MOSFET is a short channel MOSFET or a long channel MOSFET? Is there any criteria that you know? Even if you don't know any guesses, how can you say that? Can we say if it is in micrometer, then it is long channel? If it is in nanometer, then it is short? I'm talking about the channel length here. Could this be a case?
No, sir, it depends on some other factor.
Okay. Any guesses? What other factor? Like any blind guess?
Maybe with respect to the width of the depletion region. Uh,
Yeah. Oh, that is a very good or even a very correct guess. So,
Formed by the source and drains.
yeah. So let's say I'm making a MOSFET which is something like this. So this is source, this is drain. For simplicity, I'm not making gate as of now, and I'm making a MOSFET which is this. Okay, it again went. Uh, Sorry. Can you see my screen? Um, uh, Sorry, I hope I'm audible.
Yes, sir.
Yeah, yeah. So as you already said that it can be depending upon the widths of the depletion region in general. So let's say I'm making two different MOSFETs and we are applying a certain, what we do is, what we increase is we increase the drain to source voltage as we go more and more into the saturation. So if I'm increasing the drain to source voltage, this particular PN junction is going into reverse bias, right? So we'll be having more and more reverse bias. And what we have, let's say we have a symmetrical MOS, and if I do the same thing here, so can you see the difference? If these two things collide, then there we don't even have a control of the gate, because once we have this collision, we will have the depletion region and there is no control of the gate voltage and we already will have a channel. So basically the short channel MOSFETs are nothing but we can say when the depletion width of source and drain becomes comparable to the channel length. So we can call these MOSFETs as short channel MOSFETs. You need to understand this first, that the major objective of doing anything in this course is to have more and more current. More and more current will have a better device, because what we want is should have more and more current. So let's say this is a very basic equation, and for more and more current, what we can do is either we can increase this mobility. We don't have that option because we have a fixed material in the channel. Let's say we are using a silicon which has a fixed mobility, then increasing the capacitance is one of the option. I guess if you have attended the previous lecture, we discussed about this, that let me write some of the terms. So let's say IDS is proportional to mu n Cox W by L, then we have VGS minus VT, and let's say VDS is also there. So it is fixed, we cannot play with this, and this particular Cox is nothing but epsilon ox by Tox. So to increase this capacitance, we need to decrease this oxide thickness. And what will happen to the device? Something bad will happen to the device if we decrease the oxide thickness. What could be the thing that can happen if we reduce the oxide thickness? Can you tell?
Gate leakage current.
Yes, exactly. So there will be gate leakage because we will have a very thin oxide. So there will be electrons that are going to and fro from the gate to the channel. So there will be a gate leakage that can happen. So we do not prefer to even decrease this oxide thickness. What we do instead, we can have materials which have a high K permittivity, or high K materials that we call, to have more and more current. So in previous lecture, we covered a concept known as effective oxide thickness, in which we were taking about some of the high K materials, HFO2 like that, which has a epsilon relative of 25 as compared to 11.7 for silicon, or SiO2, let's say 3.9, because we are talking about oxides, so let's compare it to a certain oxide. And then the third thing that we can do is we can increase the width, but increasing the width will consume more and more area. That means more and more power consumption is there. And either we can reduce the length. So this is the best thing that industry has come up from the past hundred or thousands of years. Uh, so I guess you might have heard about the Moore's law, which says that in every 18 months or so, the number of transistors double on a chip, on a particular area that I'm talking about. So what they are doing is they are basically reducing the channel length to have that, and by reducing the channel length, we will have a certain increase in the IDS. So that is why these particular effects are coming into the picture, that I'm calling it the short channel effects, and we have certain consequences of that that are not good for the device, but we need to bear with that, and we need to see what are the things that can come into the picture. So there are several short channel effects. So let me name few. So one is the VTH roll off, the second is punch through. So these are the most of the questions that are asked in any of the VLSI interviews that you will give, because this is the most important thing that is going on right now uh, in the industry also. Then we have Dibble. Maybe I can write the full form. So then we have the drain induced barrier lowering. What else we have? We have the channel length modulation. Yeah, so these are most some of the most prominent effects that are coming into the picture. So let's see one by one what we have. So I talk about, let's say, first of all, how channel length modulation comes into the picture. Let's discuss that quickly. Sorry. Yeah. So let's say we were having a certain MOSFET. We did this exercise in the previous lecture. We have a source, we have a drain, and let's say we have a gate, and we see that the channel potential does not remain constant. It starts with a Vs certain thing which is 0 here, and we apply a certain voltage Vd here, and the effective VDS was changing something like this. So this is what the channel is, and we have this full of electrons if I'm talking about an NMOS for this case. But what happens is it does not stays like that. The effective length decreases, and we have a pinch off, which results into a channel something like this. Like we have this pinch off point. Uh, for more clarity on this, if you want, you can refer to the last week's video. This is very like straightforward. So the IV characteristics in saturation basically says that the current is independent of the VDS. But in reality, we do have a small dependence as a pinch off points. What happens is this pinch off points moves with the increase in more and more VDS. So once this moves, so what we are having is is a decrease in the effective channel length. So effectively now the channel has shrunk to this, and earlier it was something like this. So this particular thing is what we call as channel length modulation. And if I talk from a circuit designer's point of view, then this saturation mode current dependence upon the VDS has the same impact. Have you ever heard about the base width modulation? Is it covered in the course, which we do it in BJT? Is it covered? Could you please confirm uh, if if the
No, sir.
professor has covered the BJT? Okay, fine. So let's not make the analogy to that as of now. So basically, what I'm saying is, as we keep increasing this particular drain to source voltage, the pinch off points keep coming towards the source. This is what we have already seen. And basically what we are doing is we are actually altering the resistance value across the channel, because this pinch off point is going from here to here continuously, and we are having a smaller effective length. So technically speaking, what we have is VDF must have an influence, because we are having some different channels, so it should have some influence on uh, the drain to source current. And to express this, we come up with a empirical relation, as you already talked, for saturation region only. So for linear it remains same, so I'm just writing same here. But for saturation, once we have this saturation, what we get is we get this mu and Cox W by L. We had this VGS minus VT, which was saying that the VDS dependence is not there, but we have an additional factor which is 1 by lambda VDS, which is known as the channel length. This lambda is known as the channel length modulation parameter, and this is completely empirical. It does not comes from physics. So this is what empirical relation that has been given to the particular drain to source current to have this effect into the picture, that is for a um, drain voltage which is higher than the saturation. For short channel devices, this channel length modulation occurs, and that is basically that makes the drain to source current independent upon of the drain to source voltage in the saturation. We do have a certain dependence. So let's say now if this is fixed, let's say this has some 0.01 number. I'm just taking a random number for now. So now what you can say is basically this is the slope that we are talking about. Like this particular thing is what is determining the slope. So as we will having a higher and higher VGS, can we say that we have a more and more increase in the current? So let's say what I'm trying to say is, let's say VGS was zero point 0.5 in one case and VGS was 1 in one case. And for now, let's say VT is 0. It is not possible, but let's say VT is 0. So one case we have zero point 0.5 square, and one case we have 1 square, and this remains same, because what we are doing is we are keeping the lambda constant and we are sweeping the VDS. So if these things remain constant, so can you see that we will have a very high increase in current for a higher value of VGS as compared to a lower value of VGS? Can we say that?
Yes, sir.
Yeah, so basically, I guess this will answer your question what you have asked initially, that why do we have a higher amount of slope, or a sudden increase in a higher VGS values as compared to a very low value, because it is directly a multiple of this particular thing. Is it clear?
Yes, sir.
Okay, yeah, fine. So what else we have? So this is one of the effect that we have covered. Then we have, what we have is, let's say, let's talk about punch through. This is a very good thing. No, let's first discuss about the drain induced barrier lowering. Okay, so let's say I have a MOSFET. This is N plus, N plus. This is P substrate. So I guess I have, in some of the lectures I have asked you to make band diagrams and something like that stuff. So that will come handy here. So let's say this is the gate voltage. This is source. This is drain. Let's say I have not applied any of the voltage. Everything is at zero. So can you tell what will be the band diagram look like from here if I cut something like this? Any guesses how will the band diagram will look like? If you remember the band diagrams, or I have made you make these diagrams, something like this, and something. So this is something like that only. Uh, so any guesses how the band diagram will look like?
P substrate will have a higher, if you had to take only the conduction band,
Yeah.
uh, conduction band will be higher for P substrate region, and on either side it will be lower.
Okay. So what you're trying to say, something like this?
Yes.
Okay, that is good. So since I have not applied any voltage, let's say this is something like this. Okay, it does not look good. So let's say this is the Fermi level, the conduction band. So this is N, you can see clearly, and this is the line that I'm drawing is EI. This is EV, this is EV. So now similarly, if I make it for a very short channel length, by short channel I mean when this depletion region widths are becoming comparable to the channel length. So let's say if I make it here, in which I have a very large source and a large drain, yeah, something like this. So now again, if I try to make the band diagram, sorry, so can I again make the same thing, something like this? Sorry for the drawing, I guess it is bad, but just bear with it. So this is, let's say I've still not applied any voltage. I hope you are trying to understand what I'm trying to make. Is it understandable, the diagram? I have made it very bad. Is it fine? Are you able to get what I'm trying to make?
Yes, sir. Basically, the flat region is reduced in the P
Yeah,
substrate, right?
yeah. If I have depletion regions which are comparable, then the flat region is reduced. Yeah, that is what I'm trying to make.
It becomes like a conical shape.
Yeah, yeah, something like that. So now what we do in a MOSFET, we keep on increasing this drain to source voltage, right? So if I increase this drain to source voltage, what do you think will happen to this particular band diagram?
At the drain junction,
Hmm.
um, the field will be too high and will have a larger slope.
Yeah. So basically,
Depletion region increases.
yeah. So basically, it will go down, right? Because we have a more and more, as you said, the field is very high.
Yes.
So if I try to make this diagram now again with VD equals to some finite value. Sorry. So let me try to make here because I don't have space. So basically, what I can make is I have something like this. I have some flat region. Again, pardon my drawing. And what will happen? We have a certain decrease. I hope you are trying to understand that this is going at the lower side. This will remain flat. So basically, this is what the barrier is, right? Between the source and the drain, the channel. So if I apply a certain VDS, this thing will go lower. And this is what it will look like for this particular context. Now, if I do the same thing to a short channel device, what do you think will happen? So can I say that I have a very small hump, something like this, and we have a certain decrease? Are you able to understand these diagrams?
Yes, sir.
Yeah. So what you can see here, we still have a barrier if we have a certain channel length, a certain amount of channel length, so the electrons will not go directly from drain to source or source to drain in a readily manner. But once I have this barrier is almost reduced. So what we'll have, we have electrons ready that are going from drain to source. So that will basically resulting into the leakage of the current, because this is not what we want. This is happening because of a certain phenomena. So what is happening? We are having a drain induced. That is, by inducing the drain voltage, we are having a barrier lowering. This is what we call as dibble. And this only happens in short channel devices because of this particular barrier. This has a certain impact when we have a long channel devices, then we have a certain barrier. But once we have decreased our length so much that we are going away from this barrier, or we are not even having this, then we call it as a drain induced lower, barrier lowering dibble. Are you able to understand this?
Yes, sir.
Yeah. So this is now the second thing that we have covered. Uh, the third thing, that is punch through, it is similar to the dibble only. So let me try to explain punch through. I have already explained it kind of. So what is happening now? So we write punch through. So what is happening? I'm only making for a short channel. So if I'm applying a certain drain voltage, let's say this is again gate, this is source. So what is happening? We are reverse biasing it, right? So what was happening is I'm creating a certain reverse bias region. So the point where uh, a certain drain voltage, when we will achieve a point, will happen then when these depletion region will collide with each other, right? And then we will have a depletion region, and we will lose complete. We will basically lose complete control over the gate. Whether we apply the gate voltage or not, there will always be a channel because these two depletion regions have merged. Does it make sense? So basically, these two depletion regions have punched through. That is, they are collided with each other. So this is one of the phenomena that are that we call as punch through. Again, does it make sense? We'll completely lose our control over the gate, and we'll have some leakage currents because of this phenomena.
Sir, if the depletion regions merge,
Yes.
how will we have a channel? Because depletion region
Yeah.
tries to push the electrons to the source and drain respectively,
Yes.
or through the bulk, right?
Yeah.
So how will we
So
have the channel?
effectively in channel, what do we require? We require some layer of the electrons that we have, right? So we have these acceptor ions once these depletion region merge. So we have effectively kind of a inversion, right? Because we have electrons here, we have electrons here, and we have Na acceptor ions here. So I am ultimately making a complete single type of a channel which is completely negative. The inversion is happening, right? Like, it will not stop from electron going from here to here. It will never stop because it is a depletion region. As as soon as we have a availability of electrons, they will go from here to here readily. Like, there will be a continuous movement. Yes, there will be a repulsion because of this Na minus, but they have to go from somewhere to somewhere.
So, but depletion region doesn't allow any free carriers to stay there, right?
Yeah, yeah, it is not staying, it is going from here and here. So Okay, so let's say we have this p-type substrate and we have a complete depletion region. So let's say we have a body, it is still at what to say, it is still at ground. So there will be a lot of electrons which are traveling. So we will have a path for, let's say, VDB, and we will have a path for VSB, right? Right. We are basically, what we are increasing the source to bulk current, and we are increasing the drain to body current. That is contributing to the channel, and that this thing, which is very negligible magnitude, if I talk about for a normal MOSFET, this will like contribute a very similar thing as compared to a drain to source current, because all the carriers are moving towards these. We have the depletion region available directly.
Okay, sir.
Yeah. So this is what we call as punch through. What else we have? So once we have one more phenomena, which is
So just
VT.
another doubt.
Yeah, yeah, sure, sure.
You said about DB and ISB, right?
Yes,
Aren't
yes.
they leakage, body leakage currents?
Yes, these are the leakage current, but they will have some prominent magnitude now. That is what I'm saying. These all things are creating the leakage only. Like what we are discussing right now are the short channel effects. Like what are the bad things that they are causing to the device. So let's say if I started from a very basic thing which is dibble, let's say this. So this is not sorry, this is not what we want, right? But this is coming into the device.
Yes, sir.
It is increasing the leakage. Similarly, I talked about, I guess, punch through is also the same thing. But if I talk about now, if I talk about, let's say, the final thing, which is VTH roll off. So what is VTH roll off? So let's say I have N plus and N plus. So as we have already discussed, that the L effective that we are having is decreasing. So let's say L effective is decreasing. So what do you think will be the effect on the upon the threshold voltage? Do we require more or do we require less?
We need lesser. It
Okay, why? That is correct, but why?
so I cannot think of a reason right now.
Okay, so like mathematically, you can very easily conclude this. Let's say I have applied a certain drain to source voltage, which is making my L effective very less. So if I even talk about with respect to the same amount of current, so what you can see is if we have a lesser effective voltage, we also prior like simultaneously will be needing a lesser threshold voltage to have that same channel formation. So what I'm trying to say is, let's say this is your VG, this is oxide, this is VG. So I was applying a certain threshold voltage which is VTH1 for a certain channel length, which is, let's say, L1, which is let's say L1 is greater than L2, and I have got one more Vt, which is VTS2, and it is a length of L2, and L2 is less than L1. So if we have a smaller length, so can we say that we need to have a lesser threshold voltage required to achieve the same amount of current? Like this is a very basic understanding now. Because we will have a effective channel length which is lesser, then we will be requiring a lesser threshold voltage. A threshold voltage is nothing but it is depending upon the flat band. Flat band is not coming into the picture. We will have Q depletion by Cox, and finally is a surface potential. So this surface potential is the thing that is coming into the picture. We'll have effectively lesser surface potential required if we have a lesser effective length.
Yes, sir. Understood.
Yeah,
So Q depletion also plays a part here, right? Because we'll have to deplete spatially lesser region.
yeah, yeah. That is also, yeah. But the major impact that is caused is because of this surface potential only. Yeah, but yeah, Q depletion will also have some impact. That
Okay.
is correct. So this is what the decrease in the threshold voltage as the channel length decreases. This phenomenon is now called as VTH roll off. So now these are some of the prominent short channel effects that are very prominent in some of the devices. So like if you have ever heard about the technology, so do you know what is the latest technology that is right now coming into your phones? Let's say you have certain phones with you. So do you know what kind of technology that we are using currently? Any guesses?
5 nm node.
5 nm node of, any guesses for the device?
Gate all around FinFET.
Okay, so that is correct. So we now in gate all around also we have certain categories such as FinFETs, and we also have nanosheets now, nanosheet FET. So FinFET is basically tri-gate FinFET. Oh, sorry, tri-gate MOSFET, and nanosheet is quad gate you can say, or gate all around you can say basically FET. So currently, like the latest technology that we have has a 3 nanometer technology node that is in currently in iPhone 15. Okay, so I guess currently we have 4 nanometer technology node that is in iPhone 15 and 3 nanometer. Sorry, is it in iPhone 15 Pro and Max? So the latest technology that is currently in the market right now is 3 nanometer, and it is currently based upon FinFET. And next year, iPhone 17 when it is launched, so 16 also have the same 3 nanometer technology. They are claiming that they will be coming up with a 2 nanometer node, and that will be coming out first time from nanosheets. So like this is just for your knowledge. If maybe you will gain interest in all of these things, this is very interesting if you go through these things, and like if you study and if you get to know what are these things, then it is very interesting to know. So currently the best or the lowest technology node that we have in market, it is made by TSMC, and it is installed in Apple iPhones. So currently what we have is we have the 3 nanometer node which is in 15 Pro Max and 15 Pro, and 4 nanometer technology it is in iPhone 15. The 16 that is coming that has come recently is around 3, it is 3 nanometer technology node, and it is still FinFET, but from next year the FinFET is going to be replaced by nanosheet. So FinFET is something which is invented in 2014, and it is basically a huge revolutionizing thing when it happened. So we jumped from MOSFET to FinFETs, and it has taken a huge leap into the technology. I'll let you know a very basic overview of FinFET and nanosheets also. And like in a year or so, they are saying that the nanosheet will also get commercialized. So right now, what is commercialized is FinFET in each and every phone. Even the Samsung phone has, I guess, as you said, I guess Samsung has 5 or 4 nanometer node in their Snapdragon processor. I'm not sure about Androids, but this is I'm sure about. So these are the few things that might excite you if you go
So
through.
what is a node?
Sorry.
What do you mean by node, sir?
Okay, node. By node, okay, that is a good question. So let's say I'm saying 5 nanometer technology node. It does not mean, first of all, that it is 5 nanometer channel length. By channel length, I mean the gate length. I hope you are trying to understand. So it does not mean that. So we have certain technology node in which we have certain different channel lengths. So by node, what we mean is that this particular length, let's say this is L effective or LG gate length, it will be always equals to or less than that of the technology node. So like let me give you some example. Well, one example. So let's say I have a 20 nanometer technology node that come I guess few years back. It uses a gate length of 40 nanometer, and this is FinFET only. So we basically generalize a particular technology based upon a certain node. So let's say 20 nanometer will have certain nodes such as certain gate lengths such as 14, 16, 18, something like that. But the maximum it can go is 20 nanometer. and the most prominent one in 20 is 40 nanometer. So we take a certain area, maybe I guess there is a question like this in your assignments also there is a question. So these are the nodes. So it started from 3 micron. So 3 micron does not meet the channel length. Basically above micron, like some micron, what I'm trying to say is above this. So this is 1 micron, and below this it is some micron. So above micron, in general, the technology node meant the channel length, but since we are going towards these short channels, so now they no longer we call them as the channel length, but we call them a certain node. Like I'm currently talking about this. It's 40 nanometer. It will have, this is a 40 nanometer. Okay, sorry. I have given you the opposite picture. Sorry for that. I apologize. So let's say I have a 40 nanometer technology nodes, and the FinFET length that we have it, the gate length is 20. So it will not go below 14. Uh, it is, this makes sense. Sorry for the glitch. Does it make sense? Hello?
So for the 14 nanometer node,
Yeah.
the gate length will not go below that
Yeah,
specified.
below that node. Like this is what we are defining a node. It can have different gate lengths, but it will never go below 14 nanometer. And if it is going, then we need to have a newer technology node. So similarly, as you said, the 5 nanometer came around for Samsung around 2020, and that is what is, I get, the channel length was around 7 nanometer when this come. Make sense?
Is it the effective channel length?
Yeah, the see, we have a device. Let's say we are not applying any bias, so whatever the gate length that we are having is this 7 nanometer. In during the process, like during the process of having certain voltages and making of that, we do will having a certain decrease in the channel length, but ideal channel length, that is what is fabricated in the device, is 7 nanometer.
Okay, sir.
Yeah, give me a moment. Hello? 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 Yeah, hope this clears your doubt.
So why don't we make use of lower technology nodes for home appliances and for defense purposes? We see that we make use of 28 nanometer node. Why don't we make use of smaller nodes for such applications,
Home appliances, what do you mean by home appliances? Like any
like
appliance?
washing machines,
Yeah, okay. So,
etc.?
okay, give me a moment again. I'm having a call. Hello? Hello? हेलो। हाँ भैया, आपने कॉल करा था, पार्सल होगा, गार्ड को दे दो। हाँ अनंत, हाँ अनंत। क्या बोल रहे हैं आप? फ्लिपकार्ट के अंदर होगी भी दिक्कत। भैया ये जो 022.77। हाँ भैया। Yeah, sorry, made you wait. So what were we discussing? You were saying that why don't we use very small technology nodes in home appliances?
Yes, sir.
Okay, so that is a good question again. So like as we are going towards a lower technology nodes, what we are having a constraint in, we are constrained in supplying voltage. We are having a constraint in this. So for example, I okay, give me a moment. Yeah. For example, for UMC 180 nanometer, I think you might not have heard it, but for 180 nanometer technology node, we have a maximum constraint of 1.8 volt that we can go to the, but that we can apply to the device. Otherwise, it will break down or it will get destroyed. Similarly, for 40 nanometer and below, we have a constraint of VDD as zero point 0.7 volts. Like we cannot give a maximum supply voltage of over than zero point 0.7 volt as we go below 40 nanometer. So for home appliances, what they are a high voltage devices basically. If I talk about let's say a heater or let's say some washing machine also, they are basically working on high voltages. So that is why we don't go below a certain technology node. And even you are saying 20 nanometer, 28, but we majorly work with the micron devices if I talk about a very high voltage device such as washing machines. But now since the washing machines are mostly automated, so most of them are working on the chips and all, so that is why they might be going to 20 or so. But the major thing is this constraint, so that is why we are not going below a certain voltage or a node, sorry. Make
Okay, sir.
sense?
Got it.
Yeah. So yeah, like these things are more of a discussion point of view. We don't have much numericals or the things. Like these are things that are going to interest you as an audience. The lecture that we are having for now. So I guess we have covered most of the aspects. One more thing is what we have. Okay, so Moore's law is there. Moore's law I have already discussed. So let's see some of the questions that we have. Okay, so this is who formulated Moore's law and what does it predict? Quickly, let me know what is the answer. This is very easy, I guess. Okay.
Option C, sir.
Yeah, I guess this is very straightforward. I'm not uh, like consuming much time in this. So let's say this now. This is a question. I guess this is given in this year's assignment also. I'm not sure. So now it says that the evolution of various technology nodes over the years is given in the figures below. In the figure below. So we started with somewhere around 3 nanometer in around 1970, and we have went or we have came till, let's say if I make one more dot over here, let's say this is 2 nanometer, which will be coming in 2025. We are here now. So it is saying that comment on the power dissipation in the technology nodes of 250 nanometer and 90 nanometer. Hint, consider alpha as a scaling down factor for each of the nodes. Okay. So first of all, if we are going down towards the nodes, so what do you think the power consumption will increase or decrease?
Decreases.
Why do you think so that it will decrease?
We operate with lower threshold voltages.
So power consumption. What is basically power? Power is IV, right?
I
So what we are trying to do by going towards the lower nodes, we are
increase the
trying.
current.
Yeah. So what do you think power consumption will do? Do we have more power dissipation or lesser?
More.
Yeah. So first of all, as we are going towards the lower technology node, we are having more and more power dissipation because one thing you made sure that this area is constant. Moore's law has said that in this area only we are doubling the transistor. Let's say it has two transistors 70 years beyond or say 70 years ago, but now it has 2 raised to power 70 transistors, the same area. So the density has increased. We will have more and more power consumption if I talk about in this way. So what happens? So we have certain relations that for every scaling, this might have been taught in your lectures also. For every technology scaling, the power factor scales by alpha square and the capacitance vector. I'm talking about the gate capacitance. Scales by 1 by alpha. So this is the basic thing that might have been also explained in your lecture. So let's see what is the question here. So what we are doing is we are going from 250 to 90. So we need to see here. So this is, let's say, 250 and this is 90. So we have done 1, 2, 3 scaling. So let me try to write what I'm trying to say. So we went from 250 to 180 nanometer, 180 to 130, and 132, I guess 90. Yeah. So the power must have, uh, for one, it must have been increased by alpha square, for second alpha square, and for third alpha square. So what it is basically saying that P 90 will be alpha square times alpha square of P250. That will be alpha raised by 6 P250. It is asking for P90 versus P250, which is there any option like that? Yeah, option D. So you see, we are consuming more and more power just to have a very good and a better device, but we are not worried about that. We just want our device to work better and it should consume lesser and lesser area. Like in research, what we generally do, we try to optimize this power consumption. We make MOSFETs or we make circuits like that. We should have a lower power consumption as compared to any uh, any, let's say, a standard circuit. Have you heard about an amplifier? Let's say a common source amplifier is a circuit. So what we try to do is we try to optimize it such that the standard amplifier, if we compare to, it should have a lower consumption, power consumption to that of the standard. So this is what basically people do in research. A topic of research it is there, which is power optimization. So let's move forward. Okay, so we have this comment on the gate capacitance per unit area. So it is again going from 250 to 90 only. So Cox 90 will be 1 by alpha times 1 by alpha times 1 by alpha times Cox 250. So Cox 90 will be 1 by alpha cube Cox 250. Uh, okay. There's no option like that, but this will be the correct answer. Sure. Okay, so I'm making one more, which is Cox 90 will be Cox 250 by alpha cube. This will be the correct answer. So let's move ahead now. This is what we have already discussed, so please let me know the answer. You can have 1 minute. This is very straightforward now. Okay, I have one option as B. Anyone else wants to try? Okay, so as we are increasing the VDS, the effective channel length is for sure decreasing because we will have a wider depletion region. And once we have a decrease in the channel, that will increase the drain current. So which is option? There is option. Oh, which is option B? Yeah, that is correct. I hope this is clear. So let's move ahead. Okay. So we have one more question which is similar to for short and long. So let's say we have two N MOSFETs, M1 and M2. M1 has a certain length width and Tox, and M2 is also having a certain thing. The electron diffusion length is 1 micron. Choose the correct option. So it can have more than one correct option, as you can see. So let me know what can be the answer. Let's say this is A, B, C, D. You can take 1 or 2 minutes. So I've got one answer which is B. Okay, so I'm saying again, more than one can be correct. So B is M2 is a short channel MOSFET. Okay, so we'll see it in a minute. Maybe others also you can try. Yeah, you can take 1 more minute for that. Okay, so I've got one answer as A and B. That is both are short channel. I've got one answer as B and C. That is one is short, one is long. Okay. Okay, fine. Okay. So we can see that the channel length for M1 is 8 micron. For M2 it is 0.8 micron. And it is saying the diffusion length is 1 micron. So I hope you remember this diffusion length. That is, it is the collision between any electron will only happen if it is having a length more than that of 1 micron. So basically, if I try to make n plus n plus, so this length, if it is, let's say for the second case, it is 0.8 micron. So the diffusion will never happen and it will be always in a depletion region. That is a characteristic of a short channel MOSFET. Let's say I'm writing SCM. So M2 will be a short channel MOSFET, and based upon the diffusion length of M1, sorry, the channel length of M1, it will be a long channel MOSFET. So I guess M2 is short and M1 is long. Yeah, so B and C is the correct answer. Okay, so let's move ahead.
Sir, how can we say that diffusion will never happen?
Okay, diffusion will never happen means, see, the electron diffusion length means that a electron to collide with some other electron, it requires at least 1 micrometer distance for that, and the channel length is only 0.8 micron. So what I'm saying is we don't have any region so that the electrons collision will occur, and that is why I'm calling it as a short channel MOSFET.
Okay,
uh,
so before it collides, it reaches the other terminal.
yeah, it reaches other terminal. Yes.
Okay.
So okay, so is it visible, the problem? So we have a measured IV of a short channel MOSFET that is given here for L equals to L1. Now it says if the channel length is triple to 3L1, choose the correct IV. Uh, so it is like already present here. So maybe I can zoom this. So we have a certain MOSFET which was having a length L1 and now it has been tripled to 3L1. So what will be the new IV they are asking? So you can take 1 or 2 minutes and let me know your guesses. Bottom third, that means, okay, I'm getting one answer as F. Uh, is it right? You're saying bottom third means F. Okay. Anyone else? Think more if you are saying F. And the question is saying that the channel length is tripled, like it has increased three times. Okay, so let's see what we can have. Okay, so now the channel length has tripled. Okay, can you tell why did you say F?
Uh, since the channel length has tripled, the current decreases.
Yeah, that is fine.
So it will be the plot will be lower than that for L equals L1,
Yes.
and the VT also increases.
Okay, so channel length is, yeah, VT increases, right?
Mm,
You are going in the right direction. So first of all, the current will be less. That is fine. So I'm like removing these three. So either it will be A or C or F. So first thing is I on will be more. Sorry, less. Or IDS I'm writing IDS will be less. The second thing is VT. So the channel length is tripled, the VT will increase, right? And what do we have? We have this VD set, which is VGS minus VT. So if VT will increase, this VD set will.
decrease.
So what do you think the answer will be? Is it still F?
C should be the answer. C.
Okay, so you're saying C. So F should not be there because you can clearly see it is having some higher VD set. So now let's come to A or C. Okay,
But for C in the linear region, the current is higher than that of
yeah.
L1.
So is it possible?
Not possible.
Yeah. So answer would be A.
Yeah.
Yeah. So that is a very good analysis for this particular question. And the next thing
So,
is
but in that case, the overdrive voltage seems to be the same, right?
no. It is,
The saturation voltage.
yeah. It is almost same, but there is a certain difference you can see.
Okay, so for the red one, it should be lower.
For the red one, it should be lower. Yeah.
Okay.
Like there is not, it is not as scaled as it should be, but it should be something like that to be precise. Yeah. So for this, as we have discussed the reason, so now it is asking that choose a correct reasoning for your answers in the previous question. So again, it can have more than one answer. So let me know what are the possible reasons. Any guesses? This is straightforward, I guess. So I've got one answer which is A, B, and F. So I'll wait for 1 or 2 minutes more so that I'll get the answer from other, and then we'll discuss each of the option. Okay, I'm not getting any other answers. Okay, so let's see one by one and then. So the first option says that the current for the long channel MOSFET saturates at a larger VDS as compared to the short channel. So we have just seen that the VD sat will be lesser if the VTH will be higher, and VTH will be higher for the long channel MOSFET. So for the long channel MOSFET, it's saying that it is saturated at a larger VDS. Okay, for long channel is this one, and the short channel was this one. Sorry, the long channel was this one. It For the long channel MOSFET, it saturates at a larger VDS as compared to short channel. So is it opposite of that? Is it opposite? I guess this is opposite. So the long channel MOSFET reaches a critical field at larger applied biases. So this is correct. For long channel will be requiring more applied bias in the absence of velocity saturation. Yeah, so velocity saturation will not take place. So B is correct, that is for sure. Sorry. The current for the long channel MOSFET saturate at a smaller VDS as compared to the short channel. This is correct. This is Aligosa 3L1. Yeah. The long channel MOSFET reaches the critical, so this is wrong. The I1 by IO ratio for a long channel MOSFET is lower. So I1 for a long channel is lower as compared to short. So this is also wrong. I1 by IO will be better for the short one. Just don't get confused for ion by up. I'll explain these terms also. What are these things? And the current in the long channel MOSFET follows this. So this is like universal. So is it that B, C, and F are correct? Do you guys agree? I'm confused from between A and C, but B and F I can sure. I'm sure. Do we require? I guess explanation that we had for long channel MOSFET. Do we require a higher VD to saturate or a smaller VD? This is the question. Because now what I see is, I guess they are trying to make it higher. So let's think more that VD sat is VGS minus VTH. So once we have a large length, we require more gate voltage, or we have more effect on VT. Uh, Anyone coming up with some discussion? Now what I'm thinking is we might be requiring more VDS to get saturate for the case A. It is looking like that. For a larger length, we'll be requiring more gate voltage or more threshold. That is fine, but for
So,
the
but which term will dominate? VGS,
yeah,
increase in VGS, or
yeah, that is what I am also thinking. If I triple the channel length, Basically, I will require more VG, that is for sure. That will increase the VT also the requirement, but what will happen to this overall term? If I increase the channel length, then I require more VT. Sorry, it will not reduce, and more VG also. So which will dominate? That is the question. Okay, let's think more. Larger channel length means larger gate voltage. VD sat, VD sat will increase. The first option says that we require more larger VDS. That is looking like that we require larger VDS. Um, okay, I'm not sure. Do you think of anything? Anyone? I'm confused kind of at what exactly should be the answer. See, I'm sure about B and F, but I'm confused from A and C because now I'm if I zoom this out, it is looking like that for case A, I'm requiring a bit higher VDS if I'm having a long channel MOSFET. And now for a long channel, I do understand that I'll require a higher VG to get that certain VTH to reach the certain VTH, but that means the effective VD set will be also it is depending upon both the terms. So what is the case? Okay, so maybe you can think of it. Let me also think of it, and we can discuss this thing in the
So then
next.
why can't F also be a possible answer?
F is not possible because see what I'm thinking is F is not possible because there is no it has not been short channel, so it's the current should be constant. That is what I'm thinking of F for F, that there should be no velocity saturation. So we can see the current is exactly constant here, the saturation. So that is why I avoided F, but I'm still not able to understand why more VDS. Hmm. Okay, so maybe we can discuss this again in the next lecture also. I'm pretty sure that one of the thing is dominated due to some reason that I'm not sure about right now. Uh, do you have anything certain, like any reason that might justify option A is the correct answer? Okay, so we'll surely discuss this in the next lecture. Let's not just leave it. So I'll again take up this question and I'll think more that why do we have a larger VDS to saturate for the case when we have a long channel MOSFET. So let's put this
Sir, could you
into
elaborate a little more on option number B?
option number B. Okay. So it says the long channel MOSFET reaches the critical field. Yeah. So for the long channel MOSFET, we will have the absence of velocity saturation. So that is for sure, and it will only reach a certain electrical field when we have a larger VDS. So that is a straightforward thing, right? Only when we have a larger VDS, then we will have a certain electric field that is taking the MOSFET into the saturation. For larger length, we will be requiring a larger VDS to have this. Like at
Okay,
least the same thing. At least there will be absence of velocity saturation that I am sure of. So that is why I directly applied like think that B is fine. Maybe Maybe the answer is related to these things only, the velocity saturation and the mobility degradation. So let's discuss it more thoroughly in the next lecture also. And you also come up with the reason. You can mail me if you have come up with the reason today only, that why should we have a higher VDS for a higher length to saturate. Is it fine with everyone?
Yes, sir.
Yeah, sure. So let's keep these two for the next lecture also. So now this is okay. This is more of a general knowledge question. So the Samsung smartphone. So this is the question from previous year. So Janet processor, the Samsung Snapdragon. At that time, it was TSMC's 4 nanometer. So now this 4 nanometer is the technology node, not the gate length. So just leave this. Okay. So again, some question is there. Given below are two statements. So the first statement says that typically the channel length for a short channel MOSFET are much larger than the depletion width of source and drain. Okay, what is this? The channel length for short channel MOSFET are much larger. So this is wrong, right? This is completely opposite. So for short channel, we have the depletion width of the source and drain comparable to the channel length. So that is what we have read. And the current in short channel MOSFET shows significant deviations from the square law theory. So this is correct. Short channel MOSFET have certain effects. So S1 is false and S2 is true. Okay, I've got some answer. Okay, why both of them are so false?
I thought that due to leakage currents in a short channel MOSFET, you could experience some deviations.
Yeah, so it is true, right? Why are you saying it is false?
Oh, yes. Sorry, I didn't read
Yeah,
the
yeah. Okay,
question
okay.
properly.
So option B will be the correct answer. Okay, I guess that is it for some of the questions. But we will surely discuss this particular thing in the next lecture, that why larger VDS for a larger length. I'm confused right now, so let's not like go into this as of now. But we have covered at least a theoretical aspect of all the short channel effect as of in this lecture. In the next lecture, maybe I'll put some of the snapshot of these devices so that you can see that why we have a better control of the charges. Okay, please. What is this? What is parasitic BJT action and Giddle? So okay, so where have you like read about these topics?
So I read online about these topics.
Okay, nice. So I'll discuss these also. So parasitic BJT, it is basically a effect that is that comes into a MOSFET. So do you know what is BJT? Like what is a very basic BJT? BJT is nothing but a
NPN
NPN.
and PNP.
Yeah, yeah, something like that. So NPN
With a
transistor.
base
So
that is much thinner.
okay, so a very quick thing. Maybe I can discuss it. So in MOSFET, which is N plus, so we need to go a very deeper for this. So what happens once we have a very large VDS, we have impact ionization. So as we are applying more and more higher VDS, we have generation and recombination of the holes here. So let's say I have applied a very hard large VDS, that is a positive voltage. So the electron goes like this, and we have a very large body current that is coming into the pictures, because body is basically holes, right? So these holes will move from these drain to the body. So we have a phenomena known as impact ionization. I can explain it if you want a very deep understanding. So we have a phenomenon known as impact ionization, in which there are generation and recombination of electrons, and due to this increase in the body current, we have an increase in the body voltage, which triggers the source current. So basically, on increasing this body voltage, we have a very huge source current. That is what is basically BJT. BJT is so this source is acting as an emitter, drain is collector, and this is base. So BJT is nothing but IA is something equals to IC, and IC is P type. Maybe I'll have a very good explanation in the next class, because uh, see, as of now, I don't think you should go into parasitic BJT, but I will surely explain this And the second thing is gate induced drain lowering. So that is also a very simple phenomena. So we can have a discussion in the next lecture if you are interested very much. This is fine.
Okay, sir.
Yeah. Anything else as of now? Otherwise, we can dismiss and we'll meet next week. Uh, Anyone? Anything else?